Objectives for today. They're on the board. By the end of class, you should be able to, 1, explain what causes matter to change state. So why might something go from being a liquid to being a gas, or from being a liquid to being a solid? Why do those change of states happen? And you should be able to describe a heating cycle. So we're going to talk about what a heating cycle is in terms of science class, and specifically as we're talking about changing states. You should be able to describe it to me. All right, we'll get started. Recall from the previous chapter that particles are moving, and because particles are moving, they have the energy of motion, which is called kinetic energy. Solids, particles, move very little. They are in place and vibrating. As a result, they have very little kinetic energy. Gases have particles that move a lot, so their kinetic energy is going to be greater. And then liquids fall somewhere in the middle. Their particles do some moving, but not as much as gases. Particles also have potential energy. In general, objects that are closer to each other have less potential energy. Thinking about gravitational potential energy, if you use the example of a basketball, that basketball is going to have more potential energy when you're holding it up at shoulder height than it does when it's resting on the floor in the gymnasium. Because it's further away from the surface of the earth, the distance between them is greater, the potential energy is greater. The same holds true for particles. The closer two particles are to each other, the less chemical potential energy is stored between them. The greater that distance is, the more chemical energy is stored. So, because of this, solids have the least chemical potential energy of all the states of matter because their particles are very close together. Gases have particles that are spread much farther apart, and so their potential energy is greater. If you remember that thermal energy is a total kinetic and potential energy, then you'll get a little bit of insight into state change. Adding or removing thermal energy from a substance can cause a state change. Because adding or removing energy will either cause the particles to move faster or slower. When you add or remove thermal energy, you have to either add or remove potential or kinetic energy. So if you're adding kinetic energy, the particles are going to move faster. If you're removing kinetic energy, the particles are going to move slower. If you add potential energy, the particles are going to spread out. If you remove potential energy, the particles are going to move closer together, and any of these situations will cause a change in state of matter. Because remember, particles in a solid are close together and move slowly. So if you increase the speed, they spread further apart, then they're going to change from being a solid to being a liquid, and so on and so forth. Because additional thermal energy can change kinetic energy, or the speed, or potential energy, the distance, of particles, an interesting phenomenon called a heating curve occurs. So what happens is when we talk about heating, if you remember our definition of heat, heat is the movement of energy. So if we are heating something, we're adding energy to it. And in this case, the energy we're going to be adding is going to be thermal energy, either kinetic or potential. Okay? This causes this pattern to happen called a heating curve. The one we are looking at here on this page is the heating curve for water. You'll notice melting point, 0 degrees Celsius, and boiling point, 100 degrees Celsius, are marked on the graph. And you will notice that there are these interesting plateaus that form. Okay? So as we go across the graph in the x direction, we're increasing energy added. As we go up the graph, temperature is increasing. So both at melting and at boiling point, even though the amount of energy being added doesn't change, we're still adding energy, for some reason the temperature stops going up. But we're still adding energy. So what type of energy must we be adding at this point? It is thermal. It's not kinetic, so it must be potential. Okay. So let's talk through this. As particles in a solid gain this thermal energy, initially they begin to vibrate faster, meaning their kinetic energy goes up. And as their kinetic energy increases and increases, they approach their melting point. At the melting point, what happens is they start to move out of their places inside the solid. So at this point, we're now no longer increasing kinetic energy because the speed of the particle isn't increasing anymore. Now the distance between particles is increasing. And that is potential energy, not kinetic. So the total kinetic energy of the particles doesn't increase, and that is what we measure when we measure temperature. So the temperature of the substance appears to stay the same, but more and more and more of it goes from being a solid to being a liquid. When all of the particles have been spread out and have turned into a liquid, then they begin to move faster again and kinetic energy increases. And that's when you start to see a spike in temperature again. The same process happens when the substance reaches its boiling point, except this time instead of going from being a solid to being a liquid, this time they're going from being a liquid to being a gas. So again, their kinetic energy stops increasing, so the temperature stops going up, but the particles are still gaining energy. Instead of speeding up, they spread out to take up more space. They have the energy now to escape those attractive forces between particles, and they fully spread out into a gas. And when all of those particles have changed into the gas state, then you may see the temperature increase again. So the reason we see these plateaus is because at state changes, so changing from solid to liquid or liquid to solid or from liquid to gas or gas to liquid, at these state changes, potential energy is what's changing, not kinetic energy. And since temperature measures kinetic energy, the temperature plateaus during these changes. Remember back to yesterday when you did your lab in here where we tried to cool water to its freezing point, that eventually when that water started to freeze, its temperature stopped changing. You noticed that it started having the same temperature time after time after time. Okay? Which one got there first?
The one without any salt in it.
The one without any salt in it, okay? And the reason for that is, in order to go from being a liquid to being a solid, those particles have to increase their attraction to each other. And when you get those particles of salt in the water in the way, it stops that process from happening and makes the freezing temperature lower. The reverse of this process can also happen. You would just go backwards on the graph, so energy would be decreasing and temperature would be decreasing as well. But you get the same plateaus if you were cooling a gas until it condensed and then cooling a liquid until it solidified. It is possible for substances to skip the liquid phase. So substances don't have to melt and then boil or condense and then freeze. They can skip that step altogether. Okay? If something goes from being a solid straight to being a gas and skips the liquid state, we call that sublimation. You've probably only ever seen sublimation if you've seen someone using dry ice. Dry ice is solid carbon dioxide, and when you expose it to warmer temperatures, it goes immediately from a solid to a gas, and the process of doing that cools the air around it, because it takes a lot of energy, right, to do that. Cools the air around it and causes water to condense, and you get this dense fog. Okay? But goes straight from being solid CO2 to gas CO2. The opposite of this is going straight from being a gas to being a solid. This is called deposition, and this is the process by which a lot of frost forms on things. There's water as a vapor in the air, and when temperatures get cold enough, it goes straight from being a vapor to being ice crystals on a surface. It doesn't have to become a liquid first. That's deposition. In the process of state change and any other physical or chemical change, but we're talking about state change, both mass and energy are conserved. Okay? So if you boil water, it may look like the water disappears, but all of that water is still there. It's just a gas that you cannot see now. But the amount of matter has not changed. And the energy that you added to that pot of water hasn't disappeared. It's now stored in between the atoms, and when they condense, then they can release that energy. Okay, so just in a different form, it's not lost forever. Okay. All right. That should be the end of the notes for today.